Okay, welcome back everyone. The second talk of today is by Nelson Jose Rodrigues Faustino, who is an assistant researcher at the University of Aveiro and currently holds the CIDMA Chair in Hypercomplex Analysis. After completing his PhD at the University of Aveiro, Portugal in 2009, he was a postdoctoral researcher at the Center for Mathematics, University of Coimbra, CMUC, from 2010 to 13, and subsequently at the Institute of Mathematics, Statistics and Scientific Computing, IMECC, at the State University of Campinas, Brazil, from 2013 to 16, visiting professor at the Federal University of ABC, UFABC, from 2016 to 20, and integrated member of the Center for Research and Development in Mathematics and Applications, CIDMA, since 2020. He is a life member of the International Society for Analysis, its Applications and Computation, ISAC, and in 2017 was awarded an Honorary Fellowship by the European Society of Computational Methods in Sciences and Engineering, ESCMSE, in recognition of his contributions to applied and computational mathematics. And today we have a talk from him about Dirac operators of Riesz-Feller type, from probability to Hardy spaces and spectral bandwidth. The floor is yours, you may begin.
So, thank you all for the opportunity to spread out my research. I will speak about the role of Dirac operators, I would say Riesz-Feller type, but you should understand Dirac operators of Riesz-Feller type as operators defined from the point of view of spectral theory. So let me start my talk. This is the schedule of the talk. In the first part, I will explain the notion of Dirac type of operators. So probably you have seen previous talks on fractional calculus related with hypercomplex analysis. As you may notice, there are several ways to define a fractional derivative and also a fractional Dirac operator. And in this case, or in my talk, my notion is very close to the notion introduced by Riesz-Feller. On the second part of the talk, I will speak a bit about one of my contributions that it was published last year. It was the role of Paley-Wiener theorems on hypercomplex variables. I will speak about how to pass from the complex setting to the hypercomplex setting. And in the end, I will explain the importance of established functions with compact support. The third part of the talk is based on my main results, mainly generalized Bernstein spaces, the role of real Paley-Wiener theorems, and how to move from real Paley-Wiener theorems to hypercomplex Paley-Wiener theorem. And in the end, I will do some conclusions. So let me start with the introduction to my talk. Okay, this talk is based on this paper. It was published last year on Journal for Reanalysis and Application. It's a joint paper with Swanhill Bernstein from Freiburg University. And let me start to entertain you with some motivation. So, the first motivation is related with fractional derivatives and memory. So, probably when all of you try to speak about fractional derivatives, if you read a lot of papers, there are a lot of notions. So you have derivatives defined from the Fourier side, the derivatives defined in terms of the Laplace transform and other kind of transform. But the most important part is that when we pass from integer derivatives to fractional derivatives, the bottom line is the notion of memory, because and when we look for the memory, the best picture that we can think about it is just elephants' random walks, because they remember if they walk through the savannah, they remember the place when they pass for, and that's in part of the idea of a fractional derivative. And in our case, in our case we are mainly based on the fractional derivative based on the Fourier transform, in the sense that derivative can be seen as a multiplication on the Fourier transform of the function. And if we take an alpha, which is not an integer, in this case, we can encode long-term memory. So I'm not an expertise on such type of explanations, but if you are interested just to see some overview of fractional derivatives during the times, I suggest you to take a look for this paper of Stinger in Notice of IMS. So, okay, let's go now to Clifford analysis, and especially the idea is how to explain as a first glance how to work with Clifford analysis. So, first of all, the easiest way to explain is, for example, how to explain with the algebra of polynomials. So, and that's the idea. If you have the algebra of polynomials, in principle, you have two types of operators, that you have a multiplication operator, a derivation operator. And when we go from, I would say, from the real line, or I would say from the algebra of polynomials to what we can say for some sort of ladder structure based on Clifford algebras, what we need the multiplication operator. That means it's multiplication by some sort of vector. And this vector encodes the generators of the Clifford algebra, which have the similar role as the complex numbers. We also have what we call a multivector derivative, that when it's some sort of generalization of the gradient operator when it acts on the scalar. But the notion of multivector derivatives, that means that you have some sort of parallel with differential forms. For example, if such operator acts in a scalar function, it looks like a gradient. But if you take, for example, a vector field, and your Dirac operator acts on the vector field, you have just a splitting between the curl, the divergence. And I would say that using the Dirac formalism, you can, when you let it act the operator on some sort of vector field, you can, I would say, rewrite the Maxwell equations in terms of Dirac operators. Okay, let me try to explain. This is a bit about of motivation and of pedagogic for all the people from our community. In principle, in our community, we follow, I would say, on the last 30 years, we follow these the two above references. Okay, I'm not putting here the references because the idea is not to provide you a big list of references, but just to explain to people how people from different communities or from different schools, they think about hypercomplex variables. So from the Ghent school and from the Prague school, when you think about the Dirac operator, I would say the Dirac theory, in some sort of function theory, the idea is quite simple. I give you a Dirac operator, and our task is to find a Fisher decomposition and the Cauchy-Kovalevskaya extension. So it's, I would say, for this school, it's some sort of building blocks. That means that in principle, Fisher decomposition is a way to generalize the Taylor series expansion, and the Cauchy-Kovalevskaya extension is in some sort of extended a generalization of a shift of operator. If you look for a different school, for example, from the school that came from Germany, and the second motivation is based on, I think, it's based on two talks in the beginning of this seminar session. I think it's the talk of Milton Ferreira and Nelson Ferreira. It's based on the motivation given by Gulbeck and Sprossing, and the idea is a bit different. Okay, I give you a Dirac operator, and your task is to use a Borel-Pompeiu formula to solve a boundary value problem. So Borel-Pompeiu formula means Cauchy integral representation in these guys. And in this talk, I will look for them for a different way to look for, I would say, to Dirac theory or to function theory. And in this talk, I will go in, I would say, in some sort of orthogonal direction of the previous two motivations. So I will give you a Dirac type operator, and our task is to find the null solutions using singular integral representation. So, and it comes to the next question. So, okay, I think singular integrals, it looks like it's a very specific topic and probably rather technical because it comes from the theory of Calderon and Zygmunt. But for our purpose, since I think most of the people that are on this session are more of applied people, I think the easiest way to try to understand some sort of singular integral operators in Fourier analysis and I would say signal processing is just try to understand what is a Hilbert transform. Okay, so in this picture, I put some sort of frequency modulated signal. On the right picture, you can see the Hilbert transform of the signal. In principle, if you look for these two pictures on the top, you cannot see no difference between both pictures. And that means that in principle, it's some type of phenomenon that appears when we look from in terms of time and frequency. So if you cannot localize your information in time, probably it would be nice if you look for the frequency side. And the frequency side of our signal is the two pictures above. And as you can see, this is the frequencies of the signal. That means the signal on the top. And on the right, you can see the frequencies of 1/2 plus f times y, the Hilbert transform. And here, as you can see, using your eye, you can localize what is the difference between this picture and this picture. And the difference is quite simple. If you take this operator, that means it's a projection of operator on the lower half space. That means it's a boundary value of the analytic function. And as you can see, if you take a boundary value of this type, that means that you cut the negative frequencies. So that's in some sort of extent the role of the Hilbert transform. So from one side, it's a way to build an analytic function, and you can take, for example, on the real line, you can take simply a signal on the real line, and if you detect the projectional operator, you create the boundary value of your Hardy space, and using plus and minus, you can create the boundary values for the upper and the lower half space. And as you can see, how to recognize that they are boundary values. Okay, it's simply look for the frequency side. If you take the negative frequencies, means the boundary values for the lower half space. And if you take the positive frequencies, it's the boundary values of on the upper half space. So it's quite easy to recognize. And now let's move on to the generalization to hypercomplex analysis. So, and when we move to hypercomplex analysis, we can define what I call a Riesz-Hilbert operator, because such operator is a superposition of Riesz derivatives on each direction. And this operator has this singular integral representation. So singular integrals are difficult to handle, and probably it's more easy if we move to the Fourier side. So if we move to the Fourier side, that means it's a pseudo-differential reformulation. So in our case, this Hilbert transform or Riesz-Hilbert transform from the Fourier side is nothing else than this unitary vector, Clifford vector, that satisfies that the square equals 1. Well, that means that using the hypercomplex structure. That means that we can obtain very easily a generalization of the Hilbert operator on the real line. So let's move next. Next slide, it's about what people do when they're dealing with Dirac operators. The idea of Dirac operator is the first order operator that factorizes the Euclidean Laplacian, which is a scalar operator. Okay, in principle, this first notion is based, I would say, on algebraic manipulations, that it's quite nice to deal with polynomials. But if you want to look for, I would say, for function or for tempered distributions, it's more insightful if we look for the Fourier symbol, because the Fourier symbol of the Dirac operator is simply this minus I times this vector variable. And based on it, and I can now explain you the idea of Alan McIntosh. So Alan McIntosh was a former master thesis advisor of Terence Tao. Okay, it's from Flinders University. Unfortunately, he is not with us nowadays, but in the past, he provides some insightful idea to look for the Dirac operator from a different point of view. So when we look for the first definition of a Dirac operator, as I explained on the previous slide, the idea is to look for Dirac operator from some sort of like a Cartesian coordinates. So that means that you have the Dirac operator, and each component is a derivative on each xj direction. So it's a Cartesian perspective of Dirac operators. But if we think, for example, since we have the symbol of our operator, so let's think, okay, let's try to decompose the symbol in terms of spherical or polar coordinates. What will happen? So what will happen is that means that you will obtain some radial part of the symbol, and the radial part is a fractional derivative, is a raised derivative of order 1 times our Riesz-Hilbert transform, which is this unitary operator. And such construction, that means that we have some sort of polar decomposition of the Dirac operator. It comes from the factorization property. So you can find this idea on this book chapter of Alan McIntosh, and it was published 30 years ago. So now let's move for the notion before I explain my perspective of Dirac operators from the Riesz-Feller side. So let me try to explain you the idea of Riesz-Feller derivatives. So first idea to introduce derivatives came from the prominent work of Marcel Riesz. And Marcel Riesz, on 1949, he introduced some Riesz potential with symbol that corresponds to the inverse of the Riesz derivative. And few years later, with the work of William Feller, it appears a generalization of the Riesz potential. And the most important part, and this is very useful, not only for the people who works with analysis, but also with the people that works with probability, is the introduction of a skewness parameter theta. So that means that if we look for a Riesz potential is symmetric, but when we move to the Feller generalization, we put some sort of asymmetry of the distribution. When we look for the Fourier symbol of the Riesz potential and the Riesz-Feller potential, you can see that the Riesz potential in the symbol is radial. And when we look for the Feller generalization, it appears a radial symbol times a symbol that you can interpret as some sort of fractional Hilbert transform that appears in quantum optics. Application of this, the Riesz derivative is Riesz potential is to symmetric processes, but if you take some sort of asymmetry, we can also treat stable Leavitt processes. So asymmetry parameter does not exist for the Riesz potential, but for the Fellow's generalization, we need to impose some sort of constraint. That means that our theta should be chosen in what called the Leavitt-Feller Takayasu diamond. So, okay. So what is the concept? So, okay, the Fourier definition of the Hilbert transform, that means that you have, this is the symbol of the Hilbert transform, minus I times signum function. And Riesz-Feller, you have this property. And in the case alpha equals 1, theta equals 0, that means that your derivative is exactly a derivative times Hilbert transform. And these operators, they commute. And as I told you before, this phase function is nothing else than the symbol of the fractional Hilbert transform. And okay, if you take alpha equals 1, that means that you have the Cauchy distributions that it's related with the Cauchy integral form. So I'm not an expertise on this type of derivatives, but for further details, I refer to this paper of Mainardi, Luchko, and Pagnini from 2001. Okay, now I explained on the previous slide my main motivation to introduce Riesz derivatives. So let me now explain you how it works on the hypercomplex side. So that means that in order to create such type of generalization, that means that we need to amalgamate three types of notions. First of all, we need to take into account the theory of semigroups, namely the notion of Feller semigroup. We need the theory of singular integral operators. That means that we need the Riesz-Hilbert transform to encode the boundary values of your, I would say, your analytic type function. And of course, as I explained you on the previous slide, we need also some sort of theory of probability because the equation that corresponds to a generalization of the Cauchy-Riemann equation is nothing else than some sort of diffusion process. So that means that mainly to create my Dirac operator, I use these three notions. First of all, I take this Feller semigroup. I take into account that if I look from the probability side, the fundamental solution of my equation is uniquely determined by this Fourier integral formula. And the most important part is that if I take the Riesz-Hilbert transform, that means that I can build from this projection the boundary values of the Hardy space on the upper and lower half spaces. Okay. And based on it, now I can introduce my spectral formulation of my Dirac operator. So my Dirac operator from the Fourier side, as I think it's quite natural. That means that we have the radial part of the symbol, which looks like the symbol of the Riesz derivative. Here you have the phase function, and this phase function is nothing else than the symbol of the fractional Hilbert transform. And the most important feature from this construction is this splitting. Because, okay, first of all, you have that your symbol is written in this way. But if you try to rewrite in terms of the projection operators, as you can see, and this is the most intriguing part of this approach, is that our fractional Dirac operator incorporates the boundary values of the Hardy spaces. So these boundary values are indeed encoded on the definition of this action. Okay, let's now go for the next topic. The next topic is Paley-Wiener type theorems, and it's based on the work of Norbert Wiener and Robert Paley. Sorry. And this is one of the most famous books that you can find worldwide when we try to deal with theory, and I would say theory of complex variables, and I would say applications and I would say Fourier transforms. Okay, and what is the main idea of the Paley-Wiener theorems? So Paley-Wiener theorems are based on two notions. First of all, we need to look for the Fourier transform of a function. And another notion that we need to take into account when we look for the Paley-Wiener theorems is the support of your Fourier transform. And what is expected? So from the result from Paley and Wiener, you know that for a square integrable function, you say that your function has compact support contained on the ball of center 0 and radius r, if and only if the function that is written as this Fourier integral operator satisfies this exponential growth condition. So this is what the main contribution of Paley and Wiener. So that means that you can establish an isomorphism between the functions of compact support and the exponential growth of analytic function. And to create an analytic function is quite simple. On complex variables, that means that if you take a function on the real line, you simply take this shift and you create an analytic function. And then this is what we call exponential growth. So when we move to hypercomplex variables, and this was done on 2002, that means in the beginning of this century. Okay, Ku and Chan, they faced some difficulties when they tried to generalize to hypercomplex variables. First of all, is that on hypercomplex variables, a shift, if you take a shift on this vector, that means if you take a simple per vector variable shift, it does not create an analytic type function. And a way to generalize the shift is to take this exponentiation semigroup, and that means that your solution is not generated by a shift, but it's generated by what people called Cauchy-Kovalevskaya extension. And that means that on their paper, they were able to generalize that any L2 function satisfies the support condition if and only if the solution generated by the CK extension, that means Cauchy-Kovalevskaya extension of a function or of a Rn, satisfies this exponential growth condition. So this was established in this paper from Hu and Yang. A few years later, frankly, Hogan and Larkin, they tried to explain what Hu and Qian did, and they tried to explain the whole theory from this perspective of Bernstein spaces. So, and the notion of Bernstein spaces, if you look for the theory of approximation, is quite important. But okay, but before I explain the notion of Bernstein space, let's just to explain first of all the role of functions with compact support. And the first question, when you try to generalize, I would say a Paley-Wiener theory, the first question is how to create a function with compact support. Okay, You can try by yourself to handle a function with compact support, but in practice, you only need to look for some sort of topological constraints. And such topological constraints are given by the Urison lemma. This is a lemma from topology. So, and that means that if you have an open set, it looks like a ball. And if you choose a compact set contained, for example, on the ball, you know from the Urison lemma that there exists a real valued function with compact support such that the function is greater than equal than 0 and less than equal than 1 for all psi, and satisfies this condition on the compact set. Okay, some example of functions with compact support. Okay, if you try from the Fourier theory, you can take the delta function. Okay, delta function, the Fourier transform of the delta function equals 1, but you have a problem. Delta function is not a function with compact support, so we need to take some sort of modification of the delta function to have some function that you can use from the Paley-Wiener side. And some sort of modification is provided, for example, with this bump function, which is some sort of exponential function defined on the ball of radius 1. This function has compact support, satisfies this property, and the most important thing, and this is in practice, you can think like the Paley-Wiener theory as some sort of modification of global functions. Okay, that means some sort of modification of the delta function. Okay, our bump function, it converges to the delta function when we take this epsilon close to 0. And most important thing, the Fourier transform of our bump function belongs not only to L2, but for the space of distributions. Okay, and this is the picture that you can see from the Urison lemma. Okay, Urison lemma tells us that if we choose a function with compact support on the ball, that means that we need to fix from the Urison lemma. Okay, the first condition that we need to fix if we want to move from L2 space to the space of distributions, we need to fix that the support of your Fourier transform is compact. Okay, and this is a way to move from L2 functions to distributions. Okay, but some overall description of the Paley-Wiener theorems. Okay, Paley-Wiener theorems, it provides a faithful description of the space of function distributions through the growth at infinity and the support of Fourier-like transform. Okay, that means we have 90 years of research after the breakthrough approach of Robert Paley and Norbert Wiener. And we already know that the classical tools from complex analysis, such as the Pranjivan-Lindelof theorem, are not obstacle to further generalization. And this is a great achievement that most of the people obtained on the last years. That means that if we try to prove the the Paley-Wiener theorem using tools from the complex analysis, you need such theorem. But if you want to generalize to other settings, you can read this theorem, and the way to read this theorem is based on the current trends of real Paley-Wiener theorems, and we replace such theorem with the notion of Bernstein spaces. So now the natural way to think about the Paley-Wiener space, and the Paley-Wiener space is a space when P equals 2. So the natural way is to look for Bernstein spaces. So what is a Bernstein space? So a Bernstein space is a space of entire functions such that they satisfy this growth condition, and this growth condition is with respect to the LP norm. So this is this theory of Bernstein spaces you can find on both books of entire functions from 1954. And based on the notion of Bernstein spaces, we have several different ways to characterize our function space. First way to characterize our Bernstein space is based on the notion of bandwidth. That means that we can take the support on the real line from -r to r. We take the compact set, and then that means that using this compact set, if our distribution Fourier transform has support on this compact set, we prove that every LP function belongs to the Bernstein space. Okay, other way to characterize the Bernstein space is, roughly speaking, very close to the notion of Taylor series expansion. So instead, and the idea is quite simple. So instead of looking for the analytic type function, which is some sort of exponential function in the sense that it can be extended as a Taylor series expansion, so you can look for the coefficients. And the coefficients means that the derivatives of your real function. So based on it, we say that a infinity function such that all the derivatives belong to LP, it's a Bernstein, belongs to the Bernstein space if and only if you have this Bernstein inequality. And this means that each coefficient or each a derivative of your Taylor series expansion satisfies such Bernstein inequality. And this is a way to ensure that your function belongs to the Bernstein space. So this is not new. This is one idea based on the work of Nikolsky that you can find on this book of 1975. So that means that when we try to generalize Paley-Wiener theorems, so, and this is, probably I'm speaking too much, but the idea when you try to obtain such generalization, it's not only to replace one operator or a classical operator or a complex or a Cauchy-Riemann operator by some generalization. So we need to understand that the Paley-Wiener theorems involve in practice quite fields, and that means that quite notions. As I explained to you, if we want to ensure functions with compact support, we need to take a look for Urison lemma. This is a lemma that comes from topology. If we look for the characterization of the Bernstein spaces, and that means that for P equals 2, it's the Paley-Wiener spaces, that means that such characterizations came from Bernstein inequalities, and this is a result that comes from approximation theory. So when we try to introduce the notion of Bernstein spaces, so that means that we are moving from approximation theory to evolution PDEs. And later on, when we speak about functions of exponential order, this is in practice the content of the result that came from analytic function theory. So that means that in order to make this generalization, you need to look for this diagram as a clock, and that you move counterclockwise, and based on it, you will prove your result from A to B, B to C, and C to D. So what does it mean? Okay, let me explain first what is a generalized Bernstein space on hypercomplex variables. And this is part of our tour de force of our approach. So in order to define a Bernstein space, first of all, we need to fix which kind of diffusion equation we want to solve. And our diffusion equation is, I would say, some sort of x0 derivative on the real axis. And here we add the diffusion part, which is our fractional Dirac operator. We impose this initial condition because it's an initial value problem, and we need to impose this growth, this infinity condition of the function, just to ensure that our function goes to 0. And this is, in some sort of extent, it's a condition that we need to incorporate in our initial variable problem, just to ensure that our function has some sort of exponential growth. Okay, so in our case, so remember this. Okay, here we have this semigroup. The semigroup is necessary to generalize the notion of Hardy spaces. That means that you generalize the Hardy spaces by letting the semigroup on the boundary values of your function. Okay, now you have this space-fractional evolution equation. Okay, and based on it, you introduce the notion of Bernstein space related with your fractional Dirac operator as a Banach model consisted of Clifford value function, such that, first of all, to belong to this space, you are searching for solutions of your equation. You need to impose this condition, and in order to obtain a function that belongs to this space, when you take the tangential limit of your function should belongs to LP space. And okay, since we are dealing with fractional derivatives, we impose this some a growth condition. And based on it, okay, this diagram explains quite well how we generalized our result. That means that first we choose LP function. That means that you choose that means that your initial condition is a LP function. Okay, you are working with the space of distributions. Okay, and then taking the Dirac operator of Riesz-Feller type, we solve a Cauchy problem based on the Fourier inversion formula. And when we impose some sort of exponential growth condition, so that means this is how our scheme works. So you look for the solutions that satisfies the exponential growth condition. Now, in the end, you will arrive as a solution of the problem that belongs to your Bernstein space. And this is our contribution on this paper. Probably I will not bother you too much with the technical details because the result is quite technical. And these four statements of the theorem is in practice what I summarize on the picture. First of all, we impose that in order to obtain some sort of Paley-Wiener theorem, we start with functions that are compactly supported on the ball. It's based on the Urison lemma. The statement B is based on the Bernstein inequalities that can be generalized to hypercomplex variables on this way. Third one is that means it's the equivalence between B and C. In practice, as you can see, here you have the exponential or this semi-group. Okay, here you have the growth condition control in terms of the exponential. And if you compare B and C, you can roughly think that B means that we are controlling the growth in terms of the Taylor coefficients of this exponentiation. And later on, this function generated by this inner product is in practice a way to create an analytic functions on hypercomplex variables. So that means that we take some sort of inner product, we later take the exponential on F, and then if we take this inner product, you create an analytic function as you have on real variables and complex variables. So that means that in practice, these four equivalences are holds, and that means that it's using the real Paley-Wiener theorems is a way to prove this hypercomplex analog. So As I said in the beginning, Ku and Qian, they prove the hypercomplex analog, but for L2 functions. That means that functions satisfy some sort of square integrable condition. If you prove two L2 functions, in practice, you don't need to impose compactly supported constraints because you have a strong result that reads all these constraints related with the support. That means that it's the Parseval theorem. So if you move for P different from 2, that means that the compactly support condition is necessary. And this is in practice what we did. So when we prove our theorem, the equivalence from A and C, A equivalent to C, is in practice, such equivalence is in practice close to the equivalence obtained by Q and Qian for P equal to. And we use this chain of implications to rebuild the theorem, not only for L2, but for all LP functions. That means that our main contribution works for not only for function, but it works also for distributions. Okay. Second, we also look for the paper Franklin, Hogan, and Larkin. So they refined the Qian-Q construction in terms of generalized Bernstein spaces, but I would like to enhance that in this paper from Franklin, Hogan, and Larkin, they spoke about the notion of Bernstein spaces, but they never introduced the Bernstein spaces. So they roughly introduced a Bernstein space as some sort of a polyvinyl space, but they don't really take the discussion how to create it in terms of a solution of a diffusion equation. And this is one of the main contributions of our approach. Okay, and our contribution in practice was the interplay between generalized Hardy spaces and generalized Bernstein spaces. So that means that if you want to prove a polyvinyl type result in hypercomplex variables, first of all, as I explained in the very beginning, you need to understand how you can encode the boundary values of your analytic function on your fractional Dirac operator. After that, you can move to the generalized Bernstein space. So this, if you read our paper with attention, it's quite technical. You will understand that first you need to start from Hardy spaces, and afterwards you can move to Bernstein space. After that, if you can obtain some sort of equivalences like you obtain on the real line. That means that we were able to prove not only that functions of exponential growth are equivalent to take the function, the initial condition, such that the Fourier transform has compact support and is contained on the ball. We not only prove this equivalence, but we also prove that proving a polyvinyl theorem is equivalent to find a solution that belongs to the Bernstein space. So this is our contribution. We did it in our paper, and I think since I explained all the details before, that means that further details can be found on our paper. So that means that our solution is split in two parts. One belongs to the upper half space, the other one to the lower half space. And based on it, we prove this result. But okay, it's a quite technical result. It involves a lot of machinery. But probably just present 1 hour talk to explain all these things is not enough. Probably some lectures about it. Okay, but by the way, for the details you can find in our paper, and I think I will skip the conclusions, and I think we can just finishing the talk, and thanks to the audience. Thank you all.
Thank you very much for the talk. Do we have any questions or comments from the audience? You can either raise your hand in the meeting or just unmute and ask directly if you have any questions. If not, then I guess, again, we thank the speaker. This is a very nice talk, and it will be appearing online soon, maybe today or tomorrow when the recording is finished.
Okay, thank you all, and we will see you in the next time.